welcome to the channel. If you're here already with me, nice to see you here. And if it's the first time you've come across this channel, then we're going to be learning some A-level maths. I've started doing this during the lockdown times of 2020, and I've got a long period stuck at home, as lots of people have. So I thought it'd be a good chance for Year 12 to make sure they don't miss out on learning. For Year 13s to give themselves a chance to go through and revise things. We don't know what's happening with Year 13 yet. Apologies if it turns out Year 13s don't need that, but it's all good to move going forwards. And also for Year 11s going into Year 12, you might miss out on a little bit the end revision, the topics Year 8 and 9 stuff. That this stuff will allow you to have a head start going into Year 12. So that's what I'm going to be doing with you all, and let's get cracking. Today is all about connected particles and also inclined planes. Going to be looking at what happens on inclined planes, because let's head over to my screen and you will see I've already set up an inclined plane. That was something I was inclined to do earlier. No, there's no real excuse for that, is there? So we have this slope, and I have placed a 5 kilogram block on a slope of about 30 degrees. And so we need to understand that when you put a block on a slope, it looks a bit like this. Here's a slope, and here's my block. I'm going to put the block on the slope, and nothing happens. This is because in this example, there is friction on the thing. We're going to first of all assume a frictionless world where it would just fall off. So if we're first of all assuming a frictionless world, let's model the situation and let's talk about what's going on. Well, first of all, the object on the plane has an effect of gravity, but it is directly down. Therefore, it is at this angle. This effect is always going to be mg, so we're using 5 kilograms as our mass. So this would be 5g going directly down. The resistance of the object, stopping the object moving into the plane, into this inclined slope, is called r, and it goes at that direction. Now, first and foremost, if we assume that this is a smooth surface, which we're going to do for the first part of this, then once you've got a smooth surface, you can then assume this will move off in a second. When we start this thing, it will move in that direction. The reason I know that is because there is no force currently going up the slope. All forces go down. And in fact, this does nothing, so it's going to be entirely generated by this slope here. We can resolve that. Instead of resolving horizontally and vertically, we're going to resolve with respect to the slope. This tells us that this resultant force is going to be the only force that goes that way, is going to be 5g, but it's going to be in this direction. So in order to help us, let's continue this line straight here. This angle is 30 degrees. Because if this angle is 30 degrees, it will mean that that is 60. And so we can work out that's 60, and we can work out that this angle here is 30. Now, what I want to know is the exact multiple of the force we've got here, and because the angle to this direction is 30, this must be 5g sine 30. I have chosen sine 30 on purpose because sine 30 is a half, so this is 5g over 2. But we're resolving it, so are there any forces? No, that is the only force going down the slope. That is the resultant force. I'm going to call it F-res for the resultant force. We can therefore do a number of different things. If we think about our kinematics, we know that F equals ma. So we have just worked out that that is 5g over 2. So that is equal to 5a. We can divide by 5. G over 2 equals a. So a is going to equal 9.81 over 2. The acceleration of this object at the moment this block is released will be 9.81 divided by 2. So approximately 4.9 meters per second. Per second. We can then use that in all sorts of calculations, or Suvat formulas, that sort of thing. But it's not as straightforward as that, because we also have a force going, as well as going down, we have a force going up and down here. Because we also might want to know this resistance force. What is blocking it? Well, going in this direction, we've got an R, but it equals 5G cos 30. Because this is the angle we want, it's going to be included as cos. So it's 5G times root 3 over 2. We know our cos of 30. So we end up with 5G root 3 over 2. That can be worked out using our calculators. So we now are able to work out in this situation what the force preventing it sinking into the plane is, and also the initial resultant force going down the slope, and the initial acceleration. There are two things that are going to make this situation worse, more convoluted. We have friction that might get involved, and we have possibility of connected particles. And we're going to look at each in turn, but I'm going to do this one first, then we're going to look at getting friction involved. So, I will rewind. If you want to check on any of this, remember you can pause at any time, watch what's going on. Taylor, nice to see you. Juna, so Juna Churchen, the lesson for them today has already happened for age to 8 to 10. That was earlier, so you just have to look back at those lessons in the videos stream. You should be able to find links to those videos. If you look in the channel videos, you can find the videos from earlier that were for younger ages. This is all A level now. Okay, so we have here, first of all, connected particles. So when I'm making my connected particle, I'm going to put another object on it. But this, oh, didn't like that, did we? This time, at the top, we're going to have a little pulley system. Basically, we weren't happy with that coming down there, so we've got a little pulley system. And on the end of the pulley, we've got a different weight. We've got a 2 kilogram weight here and a 5 kilogram weight here. We're going to keep some things the same. We're going to keep that angle at 30 degrees, but we're going to still consider it to be smooth. We do not want to overcomplicate this too early. What this means is there will be a tension. That tension is the same at both of those objects, which allows us to find something. What I do is I consider this to be, let's focus on this section first, and then later focus on this section here. So imagine it almost as two separate sections. So my first calculations are all going to be based on this first system, then we're going to look at this system after that. And just want to make it clear to, there we go. So this first system, I believe you can draw this separately because it makes it stand out more. There's only two things going on in this system. 2G going down and tension going up. That makes this system very easy to manage. It is just going to be T equals 2G. They have to be equal to each other if it is stationary. The only thing we don't know is whether it is stationary or whether 2G is bigger. So we've got actually that the resultant force is equal to 2G minus T. So we've got a system where if it's steady, if this weight is holding that weight there, then we know that they're equal. But if it's not, then there's a resultant force. We know that the resultant force must be 2g minus t. Let's first of all imagine that it's steady. This steadiness means that we now have a value for t in the other system. So we draw the other system. Remember, you can treat each part of the system as a separate diagram in itself. And we're treating this like it's been prevented from moving. So therefore, when we resolve down here, we know that t is the thing going up the track, and that must equal anything going down, which we talked about before, being 5g sine 30. So now the tension is equal to 5g sine 30. So clearly, the only thing stopping this moving down is going to be whatever the tension is here. But if the tension is 2g, 2g can't be equal to 5g sine 30, because sine 30 is a half, which is 2.5g. You can't have 2.5g is equal to 2g. So therefore, what we have in this situation is a set of simultaneous equations where we can say that the force here is 2g minus t, and we've also got here that t is equal to 5g sine 30, or 5g over 2. Therefore, the resultant force is equal to 2g minus 5g over 2, which is equal to minus half g. This tells us if it's minus a half, I said that the resulting force was going to be going this way. So a negative means actually I was wrong. The resultant force is going to go up, not down. So the resultant force here takes the object upwards, and so it also will take that object upwards, because this whole system will move that way, but not as fast as before. The resultant force now, and we talked about this in the last example, the resultant force has been impacted by having this 2 kilogram weight that's sort of trying to hold it back. So now, if we think of our F equals ma from before, the resultant force is now only half g. And it's still going to equal 5, 6, 7 5 kilograms here. So this object has force and acceleration, so it's going to be mass times acceleration, 5 times a. So a equals g over 10. It's been slowed down an awful lot. It's only 0.98 meters per second now. But the whole point is that this connection of these particles is very important. So we're trying to identify that in an inclined plane we've got our system. You can connect particles and it can prevent things happening. What we then have is the third level, is when friction gets involved. So for the final one, a very similar example, but just to switch it up a bit, I'm going to make that 40 degrees. I have an object. This is 6 kilograms, but I've put it on a plane where friction is now involved. What that means is there is a force holding it back from falling down. We also have this connected particle. And this particle is 1 kilogram that's trying to help it back. And that's T, that's T. The friction is always mu r. And we're going to say the surface of this surface here has a friction coefficient that we're trying to work out. So we don't know what it is, but we are going to look at this system, and it's going to tell us it is holding. The friction here is holding the object. So as I mentioned to you before, there are two systems here. This system and this much simpler system. So let's first of all deal with the much simpler system. We know it's holding, and the only two forces here are 1g and t. But if it's holding, we know that t must equal 1g. Quite straightforward there. In that system, it's holding, it's not moving, therefore the tension is equal to the mass times gravity there, so it's just g. This is all very useful when we look at this system over here, because we can now say that that's 1g. And we know it's in equilibrium. This straight line here tells us that that's 40. I'm now going to resolve up away from the slope, perpendicular to the slope. R is the force going there. It allows us to ignore t because it's perpendicular. If any force is perpendicular, we can ignore it. We can also ignore mu r. So the only other force trying to get into here is going to be R equals 6, because that was 6g. 6g cos 40. So we've got R is 6g cos 40, and we are now going to say that that's the forces going that way, and they equal to each other. So we can work that out. So I quickly open up my scientific calculator, which should have been open before we started, but no harm. No, I don't want to activate a license for it. Still got 88 days of it. Wonderful. So hopefully, if I do this and then click on there, it appears. Yay! So I want to know what 6g. So let's go back to there. And we'll just do the normal maths. We are going to do 6 times 9.81 times cos 40 and we've got 9 minus, that doesn't seem right unless it's in radians. Ooh, menu. It is in radians. Now we go back, and we go back up, and we execute the same thing again. 6 45.04. All of that was probably very gripping reading. So we've got a value for R. But in this system as well, we can resolve down the slope. And I told you at the start that in this system, all of that you couldn't see. So that was good. Oh, down this slope, we have got that the R can be ignored, but we've got 6g cos 40, and that is going to be equal, that force coming down this way is going to be equal to t plus mu r. And that means 6g cos 40 is equal to 1g plus mu r. But we have a value for r, so we can say that mu r is equal to, let's move that over there, mu r is equal to 6g cos 40 minus 1g, so therefore mu must equal 6g cos 40 minus 1g all over 6g cos 40. And that should have been sine all the way. No one telling me. Because we are going down the slope, but that's the angle there, so we're always going to be using sine for when the angle is the one we don't know. There we go. We can now put all of that into our calculator, which you now can see on the screen. So we've got 6 times, we'll open a bracket here. And we've got, open bracket, 6 times 9.81 times sine 40 minus 9.81. On the bottom, we've got 6 times 9.81 and times cos 40. Now we can only do all this calculation because we know it's in static. It's not moving. It's in equilibrium. But using the friction and the connection of the particles here, we're able to see this calculation tells us that mu is 0.62. That is the coefficient of friction. So what we've done is we've combined various different things. We started off with a simple particle, a simple object, and we looked at when you put it on a slope, it has an inclination to move. We then looked at what happens when you connect it up. And when you connect it up, but you still consider it to be smooth, we have to look at 2 separate situations. First of all, we find out what the resultant force is based on the first situation. So we've got an equation, a formula for it, but we don't know what T is. But we then look at the second formula and the second equation. By resolving down the slope, we're able to work out what the tension is. That then tells us a little about what the force must be if it's being held. Obviously, there is different situations going on here. We've then what happens when friction gets involved, and all of this diagram describes what happens when the friction affects the slope and makes it more difficult for the objects to slide. Now, in general, these objects will always work together. So either the system is going to go that way, or the system is going to go that way, or it's going to hold. And in equilibrium, we know that there's a balance, so we know a lot of the forces are equal to overall, the resultant force is equal to 0. And that's where a lot of calculations can be done. You will notice in the link in the description there is some further questions you can try. Hopefully this has been useful for those people in year 12 who are still learning some of this stuff. If there's any questions, please put them in the comments below. I'm always happy to answer questions with anything that people are stuck on. Do what you want to ask me questions, and I'm more than happy. From next week, these are not going to be live streamed because there's not enough people wanting to see the live stream lesson on A level. What I'm going to do instead is I'm going to release videos, try and make them a bit more professional, clean them up a little bit, and so that hopefully that it'll be even easier to understand, because I feel that my A level stuff, it's just a little bit chatty and a little bit, as you can see, anyone who's watching it, it's a little bit complicated, and I want to make sure that it's cleaner for everyone who's watching. That's all for me. Thank you very much for joining. I've been Mr. Harris. Take care.